In the last two examples, we were given the value of the derivative of a function at a specific value for x to connect that idea to being the instantaneous rate of change of the function. Now we want to see how we actually go about constructing the definition for the derivative so that we could calculate that value rather than having it just given to us in a problem. We still want to start with the idea of the slope of the secant line, where again we choose 2 points along a curve and connect those with a straight line. To calculate that slope, we already discussed, we take y2 minus y1, the difference of our y values, over the difference of our x values. And now what we want to do is rewrite our x values. Rather than writing them in terms of x and y, we want to go back to that value h that we looked at in that interactive graph. Now what we want to do is let our first value for x, x1, be some value a. Doesn't matter what it is. And then we can define our second x value as that value a plus h. So h just representing the difference between the two x values. So we've restructured or redefined how we indicate our x values. And then based off that, we can also modify how we express our y values. Rather than it being y1 and y2, we could express this as f of a plus h minus f of a, meaning to get those y coordinates, we take those x values and plug them into our given function. Now that we've written everything in this alternate form, we can see in the denominator that our a values cancel out, leaving us with f of a plus h minus f of a all over h, where again h represents that difference between our two x coordinates. And we end up with what we refer to as the difference quotient. So really just an alternate form for writing the slope equation. We have the difference of our y coordinates divided by the difference of our x coordinates represented as this value h. Now to find the rate of change at a point, so the instantaneous rate of change of a function at a point, we consider this expression as h approaches 0, which is again exactly what we did with that interactive graph. We took that value for h and brought it closer and closer to 0 to form that tangent line. So what we're going to do is take the limit of the difference quotient as h approaches 0, and evaluating that will give us the instantaneous rate of change of a function f of x at the point x equals a. But we don't want to have to keep coming back to that limit expression and evaluating that over and over again if we want to find the instantaneous rate of change or the value of the derivative at different points. So now what we can do is take this one step further and generalize this to obtain a function for the instantaneous rate of change at any point on a given function. And what we end up doing is then calling this the derivative and defining it as the limit as h approaches 0 of f of x plus h. So now rather than using a specific value a, we just have some variable value minus f of x divided by h. Now we'll take a look at, through the course of the next few examples, how we apply that limit-based definition for the derivative to calculate the derivative function and then generate the instantaneous rate of change for a given function.